Hello, everyone. I'm waiting for the stream to spool up, but while I'm doing that, just tweeting out and everything that we are live. But hope everyone is having a good day. Hope everything's going well. Hope the course is treating well as we move into week 4 of the course. Well, ending week 4, actually, honestly. Um, and Unit 3, of course, which is what week 4 is about. Um, and kind of extending, models as opposed to just kind of talking about them. So let me tweet this out. Office hours streaming now. Oh, maybe my Twitter client seems to be having some issues. Okay, I'll go. So I got a couple of questions, obviously, to talk about today. But in the meantime, if you are watching online and would like to ask a question, feel free to post it directly into chat window. Sorry about that. My mute button. Post it directly into the chat window. And if if you want, you can tweet it at me as well. So, with that being said, let's talk a little bit about week 3. So week 3 is all about extending models. So we're gonna take a look at a couple of models and we're gonna extend them in different ways, and it'll kind of give you some idea of how to work with these models going forward. Just pulling up my notes. There is so this is kind of like the first chance that we get to really dig in, take a model someone else has built, and kind of start to play around with it. Okay, there we go. And hopefully that will be a very informative experience. Now next week is week 5, which will be unit 4, which is actually one of my favorite units. It's in fact, in some ways, it is the unit that this course was built around. Because now that you've had a chance in Unit 2 to kind of build some simple models, and in Unit 3 to expand some more sophisticated models, right? Unit 4, we're going to talk about how to build a model from the very ground up, right? And how that goes, and how you can do that. And I'll go all the way from designing a model to building a model to analyzing a model. And so in some ways, Unit 4 is kind of a small encapsulation of the whole course. Where in the rest of the course, we're going to dive into all those topics in a lot more detail. For some reason, my system is just running really slow today. I apologize. I'm trying to do two things at one time. Okay. So again, just for those of you watching, feel free to post questions in the chat. For those of you, if you want, you can tweet them at me. If you're watching this later and you can never make the chat time, then feel free to email the question to abm@complexityexplorer.org. Twitter handle is @intro to ABM. Okay? Wow, I don't know what's going on over there. Okay. So let's see. The questions I already have set up for today to talk about. So in the forum, we had a couple of interesting questions. So there was one from Abdul Qurashi. How do we know if something is more complex, generally speaking, than the other? How does the ABM perspective of complexity differ? How can we define something from an ABM perspective as being more or less complex? So there is actually, if you want to dive into complexity itself, I highly recommend going to Melanie Mitchell's course. It's also available on the Complexity Explorer website. Called An Introduction to Complexity, right? Or an overview of complexity, something along those lines. Melanie does a great job with that course, and she really kind of talks about its introduction to complexity, and she really kind of dives into these questions. I don't want to. So let's see. How can I answer this? So I'll tell you my personal definition of complex systems or complexity. And I will, and we'll go from there, okay? So I view complex systems not necessarily, or complexity is not necessarily a particular system. A system is not complex or not complex, right? A a a a problem is not does not have lots of complexity or doesn't have lots of complexity. You can view it from the lens of complexity, right? And for me, viewing something from the lens of complexity means that you're looking at the individual interactions that happen within the system and how they affect each other to create emergent properties, and then looking at how those emergent properties that arise from those individual interactions feed back to affect individual decision making, right? And so, from an agent-based modeling perspective, this is very easy to explain, right? In an agent, if you view a complex system from an agent-based model perspective, what we're talking about is how do the agents interact with each other to give rise to emergent patterns of behavior, and how those emergent patterns feed back to affect decisions, right? So, for instance, if you think about the Schelling segregation model, right, the individual decisions, right, together affect whether or not someone is going to stay in a particular neighborhood, right? Whether they've met the conditions that they need for that neighborhood, right? Um, and as a result of that, they may decide or not decide to move, right? And it's the result of all those different individual interactions that give rise to the emergent phenomenon of segregation, right? But the emergent phenomenon of segregation, the pattern that it creates, actually affects individual decision making, right? People will be happy or not happy to live in a certain neighborhood because of the segregation that's going on in that neighborhood, right? And so this is kind of what I define, and I think this comes through in the video lectures as well. This is kind of my view on complexity, right? Now, how do you define whether or not something is complex? Well, or how do you define whether or not something has more complexity or less complexity? Well, that's a different question. Now, there's a number of different ways to approach this, I think, and I don't know if I have a clear answer to this right off the bat. First of all, I guess it kind of depends upon why you're asking the question, right? Why are you asking the question as to whether or not something is more complex or not, right? If you're asking it so that you can, if you're asking it so you can determine how simple the system is to model, right? Then there are some nice solutions out there, right? So there's things like Kolmogorov complexity, right, which is talking about what's the smallest program that you can write that would generate the phenomenon that you're observing, right? There's which is kind of an interesting notion. Another notion that I really like, right, is the notion of that comes out of some of the work of Cosmo Shalizi and Jim Crutchfield, right, where they talk about these things called causal state models. And basically what they could do is they say you can take any time series type data, you can create these causal state models from them, and the complexity of the system is simply the log of the number of causal states that it takes to generate it, right? So I find that solution really compelling for a number of reasons, right? But, none of these, from an agent-based modeling perspective, necessarily match exactly. I guess you could say, from a Kolmogorov complexity type perspective, you could say that the complexity of an agent-based model is equivalent to the minimal number of lines of code it takes to create the phenomenon in the model, right? Anyways, I guess I'm punting on this question a little bit just because of the fact that I don't think you can answer this question in the abstract, right, as to how complex a system is, because it really depends upon why you're asking the question, right? So, Koreshi, if you give a chance, give us a thought as to what the context is that you want to explore that in. I think that might be helpful to go forward. Okay. There was also a longer discussion up on the forum this week on how the random seeds of the presets on heroes and cowards were determined, and there were a number of different people who chimed in. and you know, one of the questions was, how did these exact numbers come about, right? So if you look at it in the model, value in order to create the phenomenon that you see, right? So the dot has a preset seed of -1177467632. And the question is coming about, how did the modeler know which random seed would generate behavior? Was it simply trial and error? You know, what happened? Well, quite frankly, I was there when Uri Walensky generated most of these patterns, right? And I saw him do it. And essentially, he just kept running the model, right? And seeing what came about, right? And then he basically captured the random number seed and then set it, right? And so he would basically set the seed to a value, run the model, see what happened. Set the seed to another value, run the model, see what happened. He had seen these patterns before, many of them before, just from running the model without having a preset seed in it, right? And so he knew that these patterns existed. We had all seen these patterns because we played around with the heroes and cowards model. But no one knew exactly what conditions would generate them, right? And so as a result of that, he wasn't quite sure as to which models were there. And let me bring up the model just so we can be very explicit about this, right? And I literally saw him do it. He would type in seed, whatever, run the model for a while, see what happened, and if he liked it, he would capture the seed and he'd give it a name, right? I wouldn't recommend that as like a general purpose solution, right? What I would recommend doing, right, is kind of keeping. Oh, it's already up. Wow, that was kind of cool the way it worked like that. I would recommend keeping it, keeping track of your random number seeds as you're generating them, right, and kind of using those random number seeds to create the patterns. Now, of course, the interesting question becomes, if your system is highly contingent on the random number seed, right, is that actually a phenomenon you want to work with, look at, whatever, okay, in a large set. So let me see. I have to add another window capture to let you see this. And, I mean, what would be interesting, if you really wanted to explore the heroes and cowards model more, would be the reason why the random number seed generates the pattern it does, right, is because there's a particular set of choosing who's your hero and who's your coward, and there's a particular spatial location of those individuals when the system starts. Oh, that's not what I want. I want the other one. This one? Nope, not that one. Not that one. Okay, hold on a second. I'm trying to find. Oh, there. There we go. Okay. So, so as you can see, right, there's in the button command, there is this little spot that says preset -1117, right? Now, if we close that out and we go in and we look at the actual code, right, there's a command called preset. And as you can see, preset sets the random seed to that value, right? It sets the number to 68 and the personalities to mix just because that was what Uri was working with when he was playing around with those random number seeds. So you have to set all these things, right? And then as soon as we set the random number seed, right, now all of the random value, the string of random values that get chosen from then on will be exactly the same random values that were chosen at the time that Uri played around with that random seed at that value, right? And so as a result of that, we know that the model will always produce exactly the same behavior. So if you hit dot, for instance, every time I hit dot, you'll notice that they appear in exactly the same location. Every time I hit frozen, they appear in exactly the same location. And not only that, but if I hit dot and then hit go, they will move exactly the same way each time, right? And that's because the random seed guarantees that the random numbers are chosen exactly the same way, right? So a lot of times we don't actually want to set the random seed, right? And the reason why we don't want to set the random seed is we don't want the model results to be contingent upon a particular random seed, right? That being said, if we want to kind of reproduce an exact set of behavior that we saw before, like we're doing in the heroes and cowards model, then it's important to set the random seed, because otherwise you can never reproduce the behavior exactly the same, right? And so that's a very vital, important part to know. And in fact, there's also there's also it's so you can set the random seed in NetLogo, right? But there is no way to find out if you don't set the random seed. This is something I wanted to clarify. Let me pull it up. I double check this again because this changes every now and then. So I wanted to, well, it doesn't change every now and then. It hasn't changed yet, but it's something that the NetLogo developers have talked about changing. So let me bring up the description just so you can see it. So if you look in the NetLogo documentation on random numbers, random numbers, there's a very important point to realize. There's a couple of points I want to point out. If you don't set the random seed yourself, NetLogo sets it to a value based on the current date and time. There is no way to find out what random seed it chose. So if you want your model run to be reproducible, you must set the random seed yourself ahead of time, right? So that's very important to know, right? The other thing is that you can also use, if you want to do this yourself, you can use something called new seed, right? Which will actually generate a value, a random value for a random number seed generator, right? Based upon the current date and time. So one thing you can do is you can say, let my seed be new seed to get the value, and then say random seed my seed, right? And now you've captured the my seed, right? As long as you write it out somewhere so that you know what it is, right? Maybe you print it on the screen or something like that, right? And you've also been able to generate kind of a random seed to begin with, right? The other thing that I want to mention, right, is that you're only guaranteed to get those same numbers again if you're using the same version of logo, a NetLogo. Sometimes when we make a new version of NetLogo, the random number seed changes. It hasn't actually changed in a while. The actual this Heroes and Cowards model was actually written in NetLogo 5, right? And so it's still working. But it is possible that when NetLogo changes, because the random, what's called the pseudo random number generator changes, right? You could actually the values could actually change, right? Okay. So, anyways, long-winded answer to that question, hopefully, but hopefully helpful. It is interesting to talk about random number generators and how they work, and we will get into that more as we get into some of the more advanced topics in the course. Okay. By the way, again, just repeating, if you have any questions, if you're watching on the stream and you have any questions, please let me know. So another question that came about was from Eric Melo de Carvalho and Andy Smith. This is a question regarding the simple life model. Why the patches can't evaluate their neighbors and immediately update their color in one step, instead of all patches evaluating their neighbors and all patches updating their color in 2 steps. This is a very important concept and something that we will discuss in detail in Unit 5 of the course, right? So currently the model is doing what's called synchronous updating, right? And in synchronous updating, right, the code is setting it up, is waiting until it updates everything, right? And if they do it independently, right? So in synchronous updating, what happens is agents view the world, they make a decision about how they're going to act, and then they all act simultaneously, right? In asynchronous updating, agents view the world and then act without waiting for anyone else to act, right? And so what's happening and there's in particular, Erica modified the code to basically change the system. I don't think she realized she was doing this from a synchronous way of updating the world to an asynchronous way. Let's explore this one a little bit more in detail. So I'll bring it up. It's kind of hard to see in the abstract. So start that solution. Okay, so here I have the original life simple model, right? We'll make it a little bigger so you can see it better, right? And you know, the life simple model, as you remember from the talks, right, basically just says that each of these little squares lives or dies depending upon the conditions of the squares around it. And Erica, in her code, had modified a section. So in this code, there is the following. I think it's this part, right? Ask patches, set live neighbors, count neighbors with color equals green, right? And then set live neighbors to count neighbors with p colors equals green, and then update based upon that, right? So this is what I mean by synchronous update. It's doing this, and then after all the patches have figured out how many live neighbors they have, then they take actions based upon that, right? So we could just strip this part out, right? We could just take this part out right here. And what this is going to do, right? So now we have it not in 2 ask patches, but just 1. So when you do an ask patches, it loops through all the patches, has them all update live neighbors, and then it finishes, right? And then it would start the second one, and then in that one, they would all take actions based upon their live neighbors counts. By stripping this out, I'm making it part of the same one. So we're going to choose a random patch. That random patch is going to update its live neighbors, and it's going to take actions based upon it, right? And as you'll see, so if you remember, let me just show you. So this is the synchronous version, right? So in the synchronous version, right, these are the kinds of patterns you see. They're kind of complex and interesting, but kind of there is some predictability to them. Let's put it that way. Let's see what happens when we make an asynchronous update. And so now, in the previous model, each patch was looking at the number of neighbors that were live and then making a decision based upon that, right? But it was recording how many there were. Now, we're going to get kind of different behaviors, right? And as you can see, right, it still has a certain complexity to it, right? It's still kind of interesting, but it's a very different phenomenon, right? You get this, like, these green and blue stripes taking over the entire world, right? And the reason why is because rather than waiting for every agent, rather than having every patch count how many live neighbors it had and then take an action based upon it, each patch is individually counting it. And so the patch, so let's imagine that, like, you know, a patch in the middle of the world is the first one to activate, right? It counts how many it can, and it changes the state. Well, that affects the patches right around it, right? So now those patches are taking actions not based upon the previous state of the world, but based upon the state of the world with this action. Still kind of hard to illustrate in a concrete way in this model, because this model is it has some complexity to it. In Unit 5, we're going to go through a very specific way that shows you why asynchronous versus synchronous updating is important to consider when building your model. Okay. There's another discussion about, is R compulsory for analyzing agent-based models? Can we use MS Excel instead? Yes, you definitely can use Excel. You can use SAS, you can use SPSS, you can use anything that can read any code in. You can use Python, whatever you want, right? The reason why I recommend R, and the reason why we will use R in this class, right, is a number of reasons. First of all, it's free, right? And so I want to have some tool that anyone has access to. This course goes out to people all over the world, and I want to make sure that everyone has the ability to use these tools. Excel, SAS, SPSS, MATLAB, Mathematica, all those products are cost money, and some of them are actually quite expensive, right? So that's the number one reason why I'm using R, right? The other reason why I'm using R is because it is it's quickly becoming a fairly dominant form of statistical analysis in the data science community, right? And since agent-based modeling and data science often go hand in hand, agent-based models produce lots of data, data science techniques are good at analyzing lots of data, it makes sense to use those two packages together, right? The third reason, one that Chadeka pointed out, right, in the forum, is that there is a nice R NetLogo package. We won't spend too much time talking about it in this class, but you can actually run and execute NetLogo directly from R, right? And so you could actually use R as your interface to NetLogo, right? And you can, and again, you could use you can use any other package you want. And in fact, in this course, I'm going to provide you. This is not an R course, right? So I'm not going to give you everything you need to use R, but I am going to give you some sample scripts and some sample solutions for how to use R to analyze things, right? So R is not required, but highly encouraged for this particular course. Okay. Let me just go close that. Okay. Okay, let's see what the next question is that we have up for the week. And these are all. Chadeka also does a great job of kind of scouring the forums to find these questions. So these are all ones he selected for the course. So there's a question about buying the book. The book, An Introduction to Agent-Based Modeling, is available on Amazon, right? It's also available from MIT Press. This is someone in Mexico who's answering the question. I don't know how long it would get to Mexico, but I assume it wouldn't be too bad. I mean, Amazon is pretty good about shipping these kind of things. And so you'd have to check out the local Amazon dealer, probably the quickest way to do it. Currently, the book is up on Amazon, selling. I was just going to check what the current price is. So it's currently selling for $70 in the softback edition. The Kindle edition is $60, and so if you have Kindle or you have Kindle Reader on your PC, right, you can actually, I believe, I don't 100% know, but I believe you can get that instantaneously delivered to you anywhere in the world right now, right? So yeah, so fairly, I don't know if I call it cheap, right? We definitely worked with MIT Press to keep the price down. We actually deliberately went with MIT Press because they could get the price down closer to $50. The original publisher we were looking at wanted to price it like $150, and we just didn't want to do that. I won't, for sake of I won't say who that publisher was, but MIT Press was able to work with us to get that price down a lot cheaper. So we deliberately tried to make it as cheap as possible. Right? Again, the book is not required for the course, for this course, but it does make a good complement. The structure of the course, the online course, and a lot of the material is basically drawn directly from the book. And there are things in the course that are not in the book, and there are things in the book that are not in the course. Right? So, for instance, the heroes and cowards model is one of several examples that we cover in the book. But we don't cover all those examples in the course, right? There's things like simple economy and some of the other ones that we cover in the life, and other ones that we cover in the other model that are not in here. And L for all, which I cover in Unit 3, is just one of like 3 models that we cover in the equivalent chapter in the textbook, right? But then again, Unit 4, which is going to talk about diffusion of information, right? That model is completely new in this course and is not in the book at all, right? So it all depends, right? There are some complements of both. Okay. So a couple questions came in on email as well. So one person asked if this is from Sunny, asked why it's not surprising that once you set the threshold of 60, the behavior of agents converges to 60. I assume this is about the overall model. What makes us emergent rather than deterministic? Well, Sunny, you might be able to see this, obviously, and this is why we have to always, this is why, by the way, there are people who go around defining emergence as a property of surprise, right? That something is emergent only if it is surprising to me. I find that a terrible definition, right? Because it means that once I understand something, it is no longer emergent, right? And that seems silly to me, right? Like it means the word emergence loses its value, right? You might as well just replace it with the word surprising, right? I define emergence as something that is not defined at the individual level of any of the agents, but rather as an emergent property of all those agents interacting, right? There is nothing in the agents, right, that says that the property will be 60, that the value will be 60. There is a notion that each of the agents only enjoys themselves if the system has less than 60 agents. But they have no idea what all the other agents are going to do, right? If there are only 20 agents in the world, all of those agents would have fun at the bar, right? They would all go to the bar and they'd have fun every single time, even if the threshold for capacity at the bar is 60, right? So nothing in an individual agent determines what the capacity at the bar will be, right? Why is this surprising? Why is this interesting, right? That's kind of another question. And so that's why it's an emergent property. Why is this interesting, and why wouldn't you expect this, right, is another question you could ask. And the reason why you might not expect this is because Arthur's original model of bounded that he was talking about, he was criticizing the basic tenets of neo-rational economics, right? Sorry, neoclassical economics, which is rationality, essentially, right? And in perfect rationality, right, every agent has access to all the information that they need to have access to, and they have infinite amounts of computational time in order to figure out what the best solution to their problem is, right? So if you think about sometimes called homo economicus making the decision of whether or not to attend the bar, right, then every agent is exactly the same, and every agent is going to make roughly the same decision, right? Which means that either every agent is going to attend the bar or not attend the bar every week, right? So the population should be 0 or 100, right? Meaning that the median population would be 50, right? Now, the other thing that's interesting about what we see in the L for all bar problem with Brian Arthur's solution is that the population not only averages 60, but its variance around 60 is not very high, right? Like it goes up like 10 to 20 around 60 on a regular basis, right? If you were assuming a classical economics viewpoint, right, it would then the population would be either 0 or 100, and the variance would be very high, right? Another way to think about it is, what if you had a group of agents who were just randomly flipping coins about whether or not to go to the bar each time, right? Those agents, about half of them in the expectation would attend the bar and half wouldn't. Now the variance would be smaller there, but it would always be closer to 50 rather than 60, right? So maybe Sunny, maybe you're just smarter than the rest of us, so you can see the exact solution. But there are a number of reasons why the population at the bar shouldn't be 60, right? But when you have these diversity of solutions, and that reminds me, diversity is very important in this system. So let's imagine the following scenario, right? Let's imagine that we give every agent exactly the same rule to predict whether or not to go to the bar, right? Rather than having a diverse bag of solutions, right? So let's say that they take the weighted average of the last 5 weeks, right? And they use that to predict what the attendance of the bar is, right? Well, if you think about it, if every agent is using the exact same rule, even though the word 60 is hard coded into their population, the attendance at the bar won't be 60. The attendance at the bar will be either 0 or 100. So it's only when you have heterogeneous groups of agents, right, that you get this result. And that's why it's an emergent property, right? Because it's not defined in any one of the agents. It's the group of agents interacting together that get the attendance to reach 60. So let's see, another question that came up. I have a question about so there's some questions about scholarships. Let me answer that real quickly. So from Sebastian, right? There are still scholarships available. If you go to the abm.complexityexplorer.org, I believe that there is a spot where you can apply. You can click to apply for one. If for some reason you can't find it, you can always email admin@complexityexplorer.org and ask about how to apply for a scholarship. Angela had a question about. Oh, and sorry. Let me finish up with that, Sebastian. Sebastian, also there were some questions that also went on about if the course can be completed in parts, partially this year and partially in the next cohort. So you could, right? You'd have to ask admin@complexityexplorer.org how that would work out in terms of paying for the course. A lot of the course is self-paced, right? But there are two parts in particular where you are going to be facing peer review, right? So one is when you're doing the model design, and one is when you build the final model, right? And so those parts kind of have to be done synchronously across the entire course, right? So, I mean, I guess you could go through the model design review this year, right, and finish that part of the peer review, and then come back next year and go through the rest of the model, all the way to building up the model, right? The other thing you could do, right, is you could obviously, if there's parts of the course that that you want to watch later or something like that, right, you could always come back and watch them after the course is finished. All the content will be there. It's just the discussion forum won't be live. The feedback won't be live, and you won't be getting these wonderful office hours that I do, right? So that's the one concern with not doing it in the live setting. Okay. Okay. So and back to Angela's question. Angela Isabel Geraldo Suarez. Is ABM a proper tool to modeling multi-scale systems? Is it a proper tool to model transitions when those can take about 40 or 50 years? Multi-scale systems, yeah, is fine, right? It kind of depends upon what you mean by a multi-scale system, right? Like, if there haven't been a lot of multi-scale systems that have been built in agent-based models, but I don't know if that's. But I don't know of many. There haven't been many multi-scale systems, period, except outside of something like some of the global economic models and the global climate change models, right? So I don't know if that's an issue with agent-based modeling per se, as much as it is just these are not commonly built, right? But yeah, there's no problem with having like an agent that activates every 10 ticks and another agent that activates every tick, right? That's easy enough to do. You can just have something that says, if ticks mod 20 equals 0, then ask slow agents, right, to do something if ticks and then do something else every 5, right? So let me show you that real quick. I'll just build that one's a quick one to build. So let's go in here, go to new. So let's see. I can go over here. Give me 100 turtles. Let's say turtles own. If I can type. Slow. Right. Ask n of 50 turtles set slow to true. And reset ticks to go. If ticks mod 20 equals 0, ask turtles with slow forward 1 set size plus 1. Right. And then we have to do the fast turtles too. Fast turtles with fast, with not slow. Forward 1. Let's also throw in some just behavior. Right turn random 90, left turn random 90. And we won't make these ones grow, right? Okay. So, this is basically, this is going to do this is not a very interesting multi-scale model, but it's a multi-scale model where you have some turtles, half the population is only moving every 20 ticks, right? So, let me see, I need some buttons. Setup. Go. Ash turtles with slow. Oh, I have to set slow to false because otherwise it's going to default to 0 rather than a boolean. Right. Okay. Right. Oh, so obviously that works. Oh, guys, we need to tick. Okay. Set up. So as you can see, right, like half the turtles are just moving every tick, and then every 20 ticks, right, these big turtles move, right? So this kind of allows us to do multi-scale modeling, right? So yeah, so then that kind of leads into the next question: could you then do transition modeling, right, where it's 40 or 50 years? Yeah, there's nothing wrong with that. Like agent-based models, it all depends upon what the unit of ticks are and what the scale is, right? Like I could, imagine that 20 ticks is a year and 1 tick is 1/20th of a year, right? Then I could, every 1,000 ticks is 50 years, right? And I could model the changes in that way. Okay, cool. I have to actually hang up now, right? So that'll be it for today. Let me see if there's any last questions in the stream. I don't see any there. And I didn't see any come in on Twitter, though my Twitter feed has been acting really wonky today, so I apologize if I missed one that came in. For some reason, I just haven't been able to get it to load up correctly. And using my little TweetDeck app, it usually works very well for me. But that should be it for this week, right? Next week, we will be picking up with Unit 4, which, like I said, is one of my favorite units. And so I look forward to hearing your comments about that. It should go live tomorrow at some point. I always like to kind of take one last look and see if there's anything I can improve before I post it. But Unit 4 will go up live tomorrow night at the latest. Okay? Thank you all for all of your efforts and all of your work. And I look forward to seeing what you can do. Take care.